Alright, it's time to start some probability. I know, it's everyone's favorite. So we're going to learn the basic terms of probability, determine how to find a probability, determine how to find a not probability, determine how to find an or probability. So first, some basic terminology. A sample space is a set of all possible outcomes from doing an action. So let's take this instance here of having 3/4 in my hand. What are the different possible outcomes that I can get if I throw them all at the same time? Well, to create this sample space, I want to think of all the possible outcomes I could possibly have. So I could have them all land heads. Or I can have the first one land tails and the last two land heads. Or I can have the first one land heads, the second one land tails, and the third one land heads. I can have the first one, land tails, second one land tails, last one land heads. I could have the first two land heads. I could have the last one land tails. Let's see. I could have tails, heads, tails. I could have heads, tails, tails. Let's see. 1, 2, 3, 4, 5, 6, 7. I'm gonna have all tails. And we'll talk about how I knew how many were in there in 1 second. But for right now, that is my sample space. It's all the possible outcomes to this particular scenario. So let's take it a step further. So we have our different situations here. An event is a part of a sample space where we are attempting to find. If we are looking for an event of flipping 2 heads in a set of quarters, a set of 3/4, what would be contained in this event? Well, let's just, for lack of a better term, just call this A. A is 2 heads in 3/4, and we want to look back at our previous thing and look at all the instances where this occurs, and there are 3. Heads, heads, tails, heads, tails, heads, and tails, heads, heads. Okay, what about flipping 1? So just 1 head. That would also occur 3 different instances. So we would have tails, tails, heads, tails, heads, tails, and heads, tails, tails. What about no heads? Well, there's only 1 instance of that. That would be all tails. Just the 1 instance. Okay. So that's the things that would be in each event. That's what an event would be. Okay? Probability. You find the probability of an event by taking the number in the event and dividing by the number in the sample space. What is the probability of flipping 2 heads in 3/4? Well, if we go back to the sample space, we discussed how there's 8 possibilities in whole sample space. Then the event that we're talking about, 2 heads in 3/4, we go back one part of this PowerPoint. There was 3 instances of 2 heads out of 3. So our probability is 3 out of 8. Now we can shorthand this and just say, what's the probability of 2 heads? Again, this would be the exact same thing that we just talked about. Now, what about the probability of 1 head? Well, going back, we had 3 instances of getting 1 head out of a total of all possible instances of 8, which is 8. Probability of getting no heads, well, we had 1 situation where we would get no heads. So the probability of this happening would be 1 out of 8. Okay. Now, we got that. So, Now, the way I got that 8 in the first place, I knew it was from this thing called the general counting principle. It's really kind of hard to put into words. Um, if I have events that are in a combination of multiple things, I take the number of events of the first thing and multiply by the number of events to do the next thing. So, for the instance of the coins, I had 3 coins. I had coin 1, we call it coin sub 1, coin sub 2, coin sub 3. There's 2 instances to flip coin sub 1, heads and tails. 2 to flip coin 2, 2 to flip coin 3. Gives me 2 times 2 times 2 is 8. You can also kind of do this thing called a tree diagram, which not to be confused with the tree diagram probabilities that we'll talk about a little bit later. They're pretty much the same, but you can kind of see this play out like this, where we would end up with 8 possibilities, but you don't want to have to do this when you have a lot of different things going on here. Now, for instance, if I roll 2 dice, in how many ways can I roll 2 dice? Well, I have die 1, and I have die 2. It's 6 times 6, which gives me 36. So 36 different ways. So I'm going to need this for my next thing, because my next thing talks about dice. So dice continued. The event of rolling a 5 is the event that if I roll the dice, that the 2 dice will land face up on something that will add to a 5. So for instance, the dice could land on a 3 and a 2, and that would be something that adds up to a 5, the 2 dice that we have. Now these are standard 6-sided die, so you have 1, 2, 3, 4, 5, and 6 on your die. This would change if those instances would change, but everything's going to be out of 36. Now, what are the different instances that we could land on a 7? Well, 4 and 3, 3 and 4, 2 and 5, 5 and 2, 1 and 6, 6 and 1. So that gives me 6 out of 36. And if you wanted to take it further down, you could say 1 out of 6 to simplify it. It's, when I do it in my class, just to keep things simple, you don't necessarily have to do it that way, but you in the long run, you probably should. Now, a 9, again, it's out of 36. So we have 6 and 3. 3 and 6, and then we have 5 and 4, and 4 and 5. So that gives me a 4 out of 36, which can then translate to 1/9 if we want to simplify it. Probability of having a 12, well, that's pretty easy because you can only really do that one way. 6 and 6. So that's 1 out of 36. No simplification necessary. You can't even, you couldn't simplify that. Probability of an even is actually deceptively simple. I'm not going to write down all the possible ways you can have an even. All integers are even or odd. So that's 50%, 50%. So in reality, it would be 18 over 36, which is half of 36. Or 1/2, or you can just call it 50% if you wanted to. Both dice are even numbers. So you could look at it in multiple ways. You could say there are 3 numbers that are even on the first dice, 3 numbers that are even on the second dice. Whoops, that's too many of those. And get 9. So it'd be 9 out of 36, which becomes 1/4. You can also just look at the instances themselves, which I'm going to go ahead and do right now. So 2, 2, 2, 4, 2, 6, 4, 2, 4, 4, 4, 6, and then 6, 2, 6, 4, and 6, 6, which gives me also 9 out of 36, which it should, and then 1 out of 4. Okay. Alright. general probability rules. In a sample space, the probability of any one outcome is 1 divided by the total number of outcomes. Now, that might be slightly confusing. All that says is this. If I go back to my coin sample space at the very beginning, the probability of getting all heads is 1 out of 8 because it's 1 out of all possible 8. Probability of me getting specifically 1 tail first and 2 heads second is 1 out of 8. They're literally the probability of any one of these outcomes is 1 out of 8 because it's 1 out of all of the sample space. So that's what that one happens to be. The total probability of any sample space must be 100%. I use this one a lot. We use this a lot in statistics. Just says that when I add all the probabilities together in that particular sample space, it has to add up to 100%. And no probability is less than 0% or greater than 100%. Don't let your coaches fool you. You cannot give more than 100%. That is the highest one can ever possibly give. So all probabilities are strictly between 0 and 100%. And honestly, the probability of something happening at 0% or 100% is rather low. So don't think you're ever going to hit those two extremes. Okay, the not probability. What is the probability that something will not happen? What is the probability that it will not flip 2 heads in a set of 3 quarters? So the probability that of not A equals 1 minus probability of A. So this is what happens here. Let's see. Well, we've already talked about the probability of 2 heads before. That would be 3 out of 8. What if I want the probability of not flipping 2 heads? Well, it would be anything that is not 2 heads. So that's not like the extreme opposite of 2 tails. You have to think of context of heads. So what is not flipping 2 heads? Well, flipping no heads is not flipping 2 heads. Flipping all heads is not flipping 2 heads. And flipping 1 head is not flipping 2 heads. So if I calculate all of the instances of that, I would end up with 5 over 8. I can even go back and say, okay, if I look at my original probability, and I literally do not want to flip 2 heads, let me cross out the instances where I have 2 heads. I'm left with 1, 2, 3, 4, 5. 5 out of 8. 5 out of 8. Okay, so to get this number, I can just as easily do 1 minus 3/8, which is my formula here. The probability of not doing something is 1 minus the probability of doing that thing. 1 minus the probability of 3/8. What is the probability of not rolling a 7? Well, I can look at the probability of rolling a 7, which we've calculated previously to be 6 out of 36. And then all I have to do is subtract it from 1. Now I could do 36 minus 30, or 36 over 36 minus 6 over 36. And that gives me 30 over 36, or 5/6. Or you could have just done, like, you have 6 instances, you would have 30 left over. Same thing with what is the probability of rolling a 9? Well, the probability of rolling a 9, not rolling a 9 rather. So we already know from the previous thing, the probability of rolling a 9 would be 4 out of 36. So all I have to do is subtract it from 1. So we have 4 instances here. We're going to have 32 instances right here, because 4 from 36 is 32. And then let's see, if I wanted to reduce that, I would end up with 8/9. And so that is my probability of not rolling a 9. Okay. We got one more type of probability here. The OR probability. Example of this, what is the probability of rolling an 8 or having both dice be even numbers? So the way I kind of explain this is this. You have to be careful of the difference between OR and. So, if I go to the kitchen, I'm hungry. What is the difference between me wanting a apple or a banana and the difference between wanting an apple and a banana? Well, an apple or banana, I'm satisfied with either. If I go to the kitchen and get an apple, I'm satisfied. If I get a banana, I'm satisfied. If I get both of them, I'm satisfied. That's where the or comes in. The difference between here is the and. If I go to the kitchen and I want an apple and a banana, well, then I want both, and I'm not satisfied until I get both. So here I can be satisfied with one, but on the other instance, I can only be satisfied until I get both. Okay. So, for that instance, if I go down here, going back to the idea of what is the probability of rolling an 8 or having both dice be even numbers, we need to take into consideration that I'm fine with either one of these. I can roll an 8 and be fine. I can roll having both dice. I can have both dice be even and I'll be fine. Now, the formula to get this is this formula here. I'll talk about the one right below it in 1 second. But let's take a look at both of these by themselves. So, A would be rolling an 8. B would be rolling a set of even numbers. Now, we did set up even numbers before. That ended up being 2, 2, 2, 4, 2, 6, 4, 2, 4, 4, and 4, 6, 6, 2, 6, 4, and 6, 6. Okay, so that's 9. So the probability of rolling a set of even numbers is 9 out of 36. Then, what's the probability of rolling an 8? Well, we could do 4 and 4, 6 and 2, 2 and 6. We can do 3 and 5, 5 and 3. That turns out to be 5 out of 36. Now, if these things were what we call disjointed, then all we would have to do is add. Disjointed means nothing is shared in between. So the easiest way of thinking about what disjointed is taking the idea of what is the probability of you getting an A or B in any class you've ever taken. You have a probability of getting an A in the class, you have a probability of getting a B in the class, but there's absolutely, positively no way you could get both an A and a B. Since that is true and there's no way of doing both, that is a disjointed set. They will not be able to have an intersection. There's no way to do both. So that's disjointed set. So if there is no way to do both, then this is also a disjointed set, and I can just add these together. The problem with this is that this is not a disjointed set. As you can see, they both share 4 and 4, 6 and 2, and 2 and 6. So when it's a non-disjointed set, we have to do this minus probability of A and B, which means I'm just going to subtract out the probability of both of them occurring, which is 3. So 5 plus 9 minus 3 gives me 11 over 36. And that is my probability for that. Let's take a look at a couple more of these. What is the probability of 6 or 10? Well, this is disjointed because one cannot roll a 6 and a 10. It can either be a 6 or a 10. So what is the probability of rolling a 6? Well, let's see. We got 3 and 3, 2 and 4, 4 and 2, 1 and 5, 5 and 1. So that gives me 5 out of 36. What's the probability of rolling a 10? 5 and 5, 4 and 6, 6 and 4. So that gives me 3 out of 36, which gives me 8 out of 36 when I add them together, which would give me 2/9 if I wanted to really reduce that. I don't have to, but we'll do it. Odd and 9 are not disjointed. In fact, everything that you would get 9 would be in odd. So in reality, this is still just 18 out of 36. Now this is something called a subset of that. We don't talk about that in my class, but when I start talking, like going from the bottom to the top in math, I will probably start talking about subsets and stuff like that. And then the probability of 1 or a 12, which is actually kind of a trick question because you can't roll a 1 on a standard set of 2 6-sided die. So it's 1 out of 36. Finally, well, not finally, but, well, yeah, I guess the last slide. But we got all that. Let's look at this card game that I came up with. So I made this card game because, believe it or not, many people have not played around with a standard set of deck of cards. So we have a set of red, blue, green, yellow, and orange cards, all with the numbers 1 through 15. So that means there are 75 cards in total. 15, 15, 15, 15, 15, or 15 times 5. So what is the probability of getting a red card? Well, 15 out of 75. Unless you're playing soccer, which apparently it's even less than that, or more than that, depending on how dirty your players are. That's a bad joke, I guess. Or it comes out to be 1 out of 5. Okay, what's the probability of getting a number greater than 10? So there's 11, 12, 13, 14, and 15. And then there's 5 suits that would contain all of them. So 5 each of 5 suits gives me 25 over 75, which gives me 1 out of 3. Okay, a number less than 3. So the numbers less than 3 that we have are 2 and 1 of 5 different suits, because we have red, blue, green, yellow, and orange. So 2 times 5 gives me 10 over 75, or let's see, 2 out of 15. Okay, probability of getting a green card would pretty much just be the probability of getting a red card. So that would also be 15 out of 75, or 1 out of 5. Okay, probability of getting a red card or a green card. There is literally no way to get a card that is both red and green. So they are disjointed. So there are 10 red cards and 10 green cards. So we add those together, and we get 20 over 75, which gives me 4 out of 15. Not getting a blue card. So going back to that one idea before, there are 10 blue cards. So what I'm going to do is do 1 minus 10. That's not true. There are 15 blue cards. I don't know why I said 10. So 1 out of 15 over 75. Or the complete opposite of that would just be 75 minus 15, which would give me 60 out of 75, which would do, we would do 4 out of, 15, 4 out of 5 would be my answer on that one. Not getting a 15 card. So There is one 15 card in each suit, so there's 5 colors, which are the suits. So that would give me 5 out of 75. But then I don't want to get that, so I'm going to do 1 minus 5 out of 75, which gives me 70 out of 75. Which would give me, let's see, 70 divided by 5 would be 14 out of 15. Okay, so now we got some ors here. What is the probability of getting an orange card or a card greater than 12? I'm actually going to write these to the side here a little bit. 8. So we have an orange card and a card greater than 12. Okay, so if we think about it, there are 15 orange cards. And cards greater than 12, that'd be 13, 14, and 15. So that's 3 types, but 5 suits would also give me another 15. But here's the thing. There are cards that are both orange and greater than 12. In fact, there are 3 of them. So we're going to do 15 plus 15 minus 3. And if you're wondering what those 3 are, it's the orange 13, orange 14, orange 15 to be counted twice in both of these here. So we're going to do 15 plus 15 minus 3. So 30 minus 3, which gives me 27 out of 75. And both of those are divisible by 3. So 9 and, let's see, 25. I don't know why I blanked on that. Again, for my class, you don't have to reduce them if you don't want to. But since this is going over the internet, I'll go ahead and reduce them anyway. Okay, so 9 is the probability of a blue card or less than 2. Again, you got blue less than 2. There are 15 blue cards, and then there are 5 less than 2 because you had the blue one, the green one, the orange one, the yellow one, and the red one. But then you have to deduct 1 because there are 1, or is 1 rather, that is both blue and less than 2. So, and that's actually the incorrect model. Should be like that. 15 plus 5 minus 1 gives me 19, so it's 19 over 75. Last kind of challenging one. What's probably a blue card and a card less than 2? So if you remember my example of needing both in this case, you need a card that would both be blue and would also be less than 2. Well, there's only one card that exists right there. So it'd be 1 out of 75.